Look, somewhere in a lab in Santa Barbara, a machine the size of a small room, cooled down to a fraction of a degree above absolute zero, took 9 qubits, 9, and used them to simulate a wormhole. Not a metaphor for a wormhole, not a cartoon of a wormhole, a working, mathematically honest model of a tunnel through space-time, built out of quantum bits, and a signal went in one side and came out the other side, on time, on schedule, exactly the way general relativity said it should if the thing on the other end of that tunnel was real. And somewhere in the response to that paper, a bunch of very smart, very annoyed physicists said, essentially, "No, it didn't. You built yourself a toy and dressed it up in a tuxedo." Both things are true. That's the talk tonight. Stay with me, because I am not going to make this easier than it is, and if anybody tells you this is simple, they're selling you something. I've spent 50 years arguing about black holes, and I want to tell you up front, I have been wrong before, publicly, for over a decade, about one of the biggest questions in this field, and I am going to tell you exactly how and why, because the way I was wrong is the doorway into everything I want to explain tonight. This isn't going to be a highlight reel. This is going to be the actual argument, brick by brick, the way it really happened, the way it's still happening. You're probably thinking right now that a wormhole is science fiction, a shortcut through space, the kind of thing that gets you from one galaxy to another in an afternoon instead of 10,000 years. I understand why you think that. Every movie you've ever seen with a wormhole in it wants you to think that. Here's what's really going on. Yes, wormholes are a real, legitimate solution to Einstein's equations. Einstein himself, working with Nathan Rosen in 1935, found that if you take two black hole solutions and glue them together at their throats, you get a bridge. We still call it an Einstein-Rosen bridge, connecting two separate regions of space-time, or possibly two remote regions of the same space-time. The mathematics is completely legal. General relativity doesn't forbid it. But, and this is the part Hollywood skips, you cannot send anything through it. Not a person, not a photon, not a whisper. The geometry pinches shut faster than light can cross it. Anything that tries makes it in and gets crushed before it gets out. It's a bridge you can fall into and never leave. For most of the 20th century, that was the end of the conversation. A wormhole was a mathematical curiosity, a beautiful, useless corpse of a solution, interesting to write papers about and completely irrelevant to physical reality, because nothing could ever cross one. Now here is where it gets strange. In 1935, that same year, Einstein was also working with Boris Podolsky and Nathan Rosen on a completely different problem, what we now call the Ipar paradox, about entangled particles. Two particles, prepared together, then separated by any distance you like, a few meters or a few light years, and yet measuring one instantly tells you something about the other. Einstein hated this. He called it spooky action at a distance, and he was trying to use it to prove quantum mechanics was incomplete, that there had to be hidden variables, some deeper, honest mechanism underneath the spookiness. He was wrong about that. Bell's theorem and about 60 years of experiments since have nailed that coffin shut. But notice something remarkable sitting right there in the historical record. In the very same year, from the very same man, we got two papers that looked like they had absolutely nothing to do with each other. One about bridges in space-time, one about entangled particles. Wormholes and quantum entanglement, born as twins and then estranged for 77 years, filed in completely different departments of physics, taught in completely different courses, cited in completely different literatures. Nobody thought to ask if they were actually the same paper wearing two different coats. That's the part that should bother you. Not because it's a cute coincidence. Physics doesn't care about cute. But because it turned out not to be a coincidence at all. Here's the assumption I want to demolish first, the one almost everyone in this room is carrying around without knowing it. The assumption that space-time is the fundamental stuff of the universe, and that quantum mechanics is something that happens inside space-time, like weather happening inside a room. Space is the container, quantum fields are the contents. That picture is intuitive. It's how Einstein thought about gravity. It's probably how you think about the universe right now, this evening, sitting in these seats. And it's wrong. Not wrong like a small correction, wrong like the container is made out of the contents. Space-time itself, the actual geometric fabric you're sitting inside of right now, appears to be built out of quantum entanglement, not sitting on top of it. Built out of it, the way a wall is built out of bricks, except the wall is three-dimensional space, and the bricks are pairs of entangled quantum degrees of freedom. I want to walk you to that conclusion properly, because if I just assert it, you should not believe me, and Sagan. Carl, God rest him, used to say the same thing to his students. Extraordinary claims, extraordinary evidence. So let's build the evidence, brick by brick. Start with the holographic principle, because everything tonight rests on it. In the early 90s, Gerard Hooft and I, independently and then together, started asking an uncomfortable question about black holes. Jacob Bekenstein and Stephen Hawking had already shown something bizarre. A black hole has entropy, and that entropy, a measure, roughly, of how much hidden information is packed inside, is proportional not to the volume of the black hole, the way entropy works for literally everything else you've ever encountered, a gas, a liquid, a block of iron, but to the area of its event horizon, the two-dimensional surface. Think about what that means for a second, because most people say the words and don't feel the weight of them. If I have a sphere of gas twice as wide, its volume goes up by a factor of 8, and its entropy, the number of ways you could rearrange its microscopic insides and have it look the same from outside, goes up by roughly a factor of 8 too, because you've got 8 times as much stuff to shuffle around. That's how the world works everywhere, except at a black hole's horizon. There, doubling the radius only quadruples the entropy, because area scales as radius squared, not radius cubed. The maximum amount of information you can pack into a region of space isn't set by how much space is inside it. It's set by the area of its boundary. That single fact, the Bekenstein-Hawking entropy formula, is the most information-dense 4 inches of physics I know, and it took the field the better part of 2 decades to be dragged, kicking, into taking it seriously as a general statement about nature rather than a weird black hole footnote. Hooft and I pushed the idea to its logical, uncomfortable conclusion. If a black hole's information content is bounded by its surface area, maybe that's true of any region of space whatsoever. Maybe the description of everything happening inside any volume, this room, your body, the observable universe, can be fully encoded on a surface enclosing that volume, like a hologram. You've seen a hologram on a credit card, that shimmering little sticker that shows a 3-dimensional image when you tilt it, even though the information is stored on a flat 2-dimensional film. We propose that the universe works the same way, structurally, not as a metaphor, but as a literal statement about where information lives. The 3-dimensional world of stuff you can touch is, in some deep and still not fully understood sense, a projection of information that actually lives on a boundary, 1 dimension down. In 1997, a young Argentine physicist named Juan Maldacena made this precise, in a paper that I'd put on the short list of the most important physics papers of my lifetime. He found an explicit, working example. A toy universe, but a rigorously defined one, where you could actually construct the hologram and the holographic image and check that they match. On one side, a particular curved, negatively curved space-time called anti-de Sitter space, with gravity living inside it, including black holes. On the other side, living on the boundary of that space, a conformal field theory. Ordinary quantum mechanics, no gravity at all, particles interacting the way particles interact in an ordinary quantum field theory, the kind you'd find in a particle accelerator. And Maldacena showed these two descriptions were exactly, mathematically equivalent. Not similar, not analogous. The same physics, written in 2 different languages, one with gravity and one without, one in the bulk and one on the boundary. We call this the ADS/CFT correspondence, and it is, right now, the closest thing theoretical physics has to a working theory of quantum gravity. Because on the boundary side, you just have ordinary quantum mechanics. No infinities, no paradoxes, well-defined, computable. And yet somehow it's secretly describing curved spacetime, black holes, even the formation and evaporation of black holes, happening, 1 dimension up. I remember exactly where I was when I understood what this meant, because it took me longer than it should have. I want to be honest about that, because false modesty is its own kind of dishonesty, and real modesty means admitting the actual timeline. I was slow. The paper is dense. The argument is subtle. And for the first year or so, I thought of it the way most of the field did. A beautiful, exotic result about a special corner of theory space. Interesting for string theorists. Not obviously a statement about how our actual universe works, since our universe isn't anti-de Sitter space. It's expanding, not the fixed, negatively curved geometry Maldacena used. It took sustained arguing, in seminar rooms, at blackboards, over bad coffee, with people who understood it faster than I did, before the penny dropped. This wasn't a curiosity. This was a worked example of a completely general principle. Gravity, space-time, geometry itself. Emergent. Built from something else. Built from quantum entanglement between the degrees of freedom sitting on that boundary. Now here's where it gets strange, the second time tonight. And this is the one that actually connects the two threads I started with. The wormhole and the entangled pair. If space-time is built from entanglement, then the most basic building block of geometry should correspond to the most basic unit of entanglement, an Epper pair. Two entangled quantum degrees of freedom, correlated, connected, with no geometric distance necessarily separating them at all, since they don't even have to live in the same place. What happens if you have two entangled black holes? Not two black holes near each other in the same spacetime. Two black holes described by boundary theories that are maximally entangled with each other, in the specific thermal sense that comes out of the mathematics, what's called a thermofield double state. Juan Maldacena worked this problem out in 2001, and the answer is one of the strangest sentences I have ever gotten to say in a physics lecture. The bulk, gravitational description of two maximally entangled black holes is a single eternal wormhole connecting them. Two black holes, entangled. One wormhole, connecting them. Entanglement on the boundary. Bridge in the bulk. Same object. Two languages. That is the moment the two 1935 papers stopped being estranged twins. Brian Swingle had done beautiful, independent work in 2009 building explicit tensor network models of how entanglement structure could geometrically knit spacetime together, degree by degree, which gave us a concrete toy mechanism for how this actually works, brick by literal brick. And in 2013, working with Juan, I put a slogan on the whole thing. Mostly because physicists, like everyone else, remember slogans better than equations. Equals Eper. Einstein-Rosen bridges. Wormholes equal Einstein-Podolsky-Rosen pairs. Entanglement, not are related to, equal. The conjecture is that any two entangled systems, anywhere, black holes or otherwise, are connected by some kind of wormhole-like geometric structure, even when that structure is so quantum, so far from any classical notion of a smooth bridge, that it has no useful description as a traversable tunnel you could fly a ship through. Entanglement just is geometric connection, wearing a different outfit depending on which side of the correspondence you're standing on. I want to give you the honest version of my own history here, because this is the part where I fought, Stephen, and lost some rounds and won others, and where I was flatly wrong for years about something adjacent to all this. In the mid-90s, Stephen Hawking and I were on opposite sides of what the press eventually called the black hole war, over the question of what happens to information that falls into a black hole. Hawking's calculations showed black holes radiate. Hawking radiation, one of the great results of 20th century physics. And that this radiation appeared to be exactly thermal, with no information in it at all about what fell in. A book falls in, the black hole evaporates completely over unimaginable time, and out comes featureless thermal noise. Hawking's conclusion: information is destroyed. Genuinely, permanently gone, violating one of the most sacred principles in all of physics, that quantum mechanics preserves information, that the universe doesn't have a shredder. I thought that was catastrophically wrong, and I spent the better part of 2 decades trying to prove it, developing what I called black hole complementarity, the idea that information both falls into the black hole from the perspective of someone falling in, and comes back out in the Hawking radiation from the perspective of someone staying outside, and that there's no contradiction because no single observer can ever check both accounts against each other. It was a strange, uncomfortable resolution, and it took the field a long time to accept it, myself included, wrestling with whether I actually believed my own argument or was just defending a position out of stubbornness. Hawking conceded the war in 2004 at a conference in Dublin, buying John Preskill the promised encyclopedia. Information gets out. I was right about that. But here's my honest confession, the wrong turn. For years afterward, I underestimated how violent the resolution would have to be at the level of the horizon itself. Complementarity said everything was fine from every individual observer's point of view, smooth sailing, no drama at the horizon. Then in 2012, Ahmed Almheri, Donald Marolf, Joe Polchinski, and James Sully. The AMPS collaboration showed that complementarity, as I'd defined it, was actually inconsistent. You couldn't have smooth space-time at the horizon, unitarity of the outgoing radiation, and the equivalence principle all survive together. Pick 2 out of 3. Their proposed way out was brutal. A firewall. A wall of high-energy radiation sitting right at the horizon that would incinerate anything falling through, violating Einstein's equivalence principle, the idea that free fall should feel like nothing at all, right at the exact place general relativity says it should feel like nothing at all. I did not want to believe this. I fought it. I fought it hard. In papers, in talks, in an email exchange with Polchinski that got heated enough that people still bring it up to me at conferences. And here is the honest part. I don't think the argument is fully settled today, this evening, right now, in this room. What I do think, what most of the field has converged toward, is that equals Epper is actually the resolution, or at least the right direction toward one. If the entanglement between the black hole and its Hawking radiation is itself geometric, a wormhole, connecting the interior to the radiation that's flown arbitrarily far away, then there's no firewall required, because the interior isn't cut off from the exterior information at all. It's threaded through it by a bridge made of the very entanglement AMPS was worried about. That's not a settled proof. That's a research program, still active, still contested, and if anyone tells you the black hole information problem is closed and filed away, they are not telling you the truth of where this field actually stands. Now, let's get to the part that made headlines. Us scientists in shock. A quantum computer confirms the impossible. Let's take that claim apart, honestly, because it deserves better than a headline. If equals Epper is right, if entanglement really is geometric connection, then here's a testable idea. Build a small quantum system on a real, physical quantum computer that reproduces the entanglement structure of 2 black holes connected by a wormhole using the Psych model, the Sachdev-Yekitayev model, a system of Majorana fermions that's known to be holographically dual to a nearly adds 2 black hole geometry, one of the cleanest toy models we have for quantum gravity in the lab. Prepare the system in a thermofield double state, entangling 2 copies of it, the 2 sides of the wormhole. Then send a signal in, on one side, and check whether it emerges on the other side. And crucially, check that it emerges with a particular pattern of timing and behavior that would only make sense if it had genuinely traveled through a gravitationally curved wormhole geometry, rather than just leaking through by some boring, non-gravitational quantum channel. In November of 2022, Daniel Jafferys, Alexander Zlokapa, and their collaborators, working with Google's quantum processor, did exactly this, using 9 qubits to encode a machine-learned, sparsified version of the Psych Hamiltonian. They sent a message in. It came out the other side. And the timing, the specific dynamical signature of the teleportation, matched what you'd expect from a traversable wormhole, not from an ordinary decoherence channel. It was published in Nature. And yes, I was one of the people cheering, because in some real sense, this was the first laboratory signature. However small, however toy, however far from an actual astrophysical black hole, of quantum gravity, of equals Epper, of holography itself, made manifest in a device you could hold in 2 hands. Here's the moment I promised you. the one where I owe you my genuine, unresolved discomfort, because I think it's more valuable to you than false confidence. Within months, a group at Berkeley, Bryce Coburn, Thomas Schuster, and Norman Yao, published a sharp, careful critique. Their argument, in essence, the Hamiltonian used in the experiment was machine-learned to be sparse. Only a handful of interaction terms, 5 fully commuting terms among 7 Majorana fermions, specifically so it could run on a 9-qubit device with current hardware. But a Hamiltonian that sparse and that commuting, they argued, is so far from the genuinely chaotic, scrambling dynamics that real psych physics and real black hole physics requires, that the teleportation signal you get out of it doesn't actually demonstrate gravitational, wormhole-like behavior at all. It demonstrates a much simpler, non-gravitational quantum circuit identity that happens to mimic the same output pattern. In their words, essentially, you can build something that walks like a wormhole and quacks like a wormhole using nothing more exotic than an unentangling teleportation trick. No genuine gravity required, no genuine chaos required. Same headline result. Completely different, deflationary explanation. I am not going to stand up here and pretend that debate is resolved, because it isn't, and I would rather you leave this room knowing an honest, open question than a false, comfortable answer. The Jaffere's Lokapa side has pushed back, arguing the learned Hamiltonian retains enough of the relevant structure to count, that the criterion Coburn, Schuster, and Yao use for genuine scrambling is itself too strict and rules out signals that any real near-term quantum computer, with only a handful of noisy qubits, could ever produce. This is what a live scientific argument actually looks like from the inside. Not two sides screaming past each other, but two groups of serious people agreeing completely on the mathematics of what was computed and disagreeing sharply on what that computation is entitled to claim about nature. That's not embarrassing. That's the field working exactly as it should. What should genuinely unsettle you, and it unsettles me, productively, is how thin the ice still is beneath the phrase quantum gravity in the lab. We are years, maybe decades, from a quantum computer with enough qubits and enough fidelity to run a version of this experiment large enough that nobody could offer the Berkeley objection, where the Hamiltonian is provably chaotic in the way real gravity demands rather than a clever, minimal circuit dressed up to look the part. Until then, what we have is a genuine, important proof of principle, that the mathematics of equals EPAR can, in principle, be probed on real hardware. Sitting right next to a genuine, unresolved question about whether any single experiment run so far has actually crossed the line from simulating the equations of holography to demonstrating something that deserves to be called, without qualification, a wormhole. Let me give you the thought experiment that I think makes the stakes of all this vivid, physically concrete, not hand-wavy. Imagine 2 rooms, sealed, on opposite sides of the universe. In each room sits an observer with access to 1/2 of a maximally entangled pair of quantum systems. The 2 boundary theories of our eternal black hole thermofield double. From inside either room, running any experiment you like on your half alone, you will find pure, structureless randomness. Flip a quantum coin 1,000 times, get 1,000 random results. No pattern, no signal, nothing you could use to communicate. That's what entanglement looks like locally. Noise. But if equals EPER is literally true, and not just a useful bookkeeping device, then those 2 rooms are connected, right now, by a real geometric structure, a wormhole, threading between them through some higher dimensional bulk that isn't part of either room's ordinary spatial description. You cannot use it to send a signal faster than light. The wormhole is non-traversable in its natural, undisturbed state, exactly like Einstein and Rosen's original solution, exactly obeying causality. But under the right controlled perturbation, the kind engineered in that Google experiment, you can, in principle, send something through it, provided you're willing to accept that sending something through a wormhole and exploiting quantum teleportation using shared entanglement might be 2 descriptions of the exact same physical process, one gravitational, one quantum informational, equal, not merely related. I want to fold in the second thought experiment now, because it's the one that made this whole idea intuitively land for me, decades ago, before Maldacena, before equals Epper had a name. Imagine you're an observer falling into a large black hole, large enough that tidal forces near the horizon are gentle, so you don't get spaghettified on the way in. You just cross the horizon smoothly, feeling nothing unusual, exactly as the equivalence principle demands. From your perspective, nothing dramatic happens. You cross, you continue falling, eventually you hit the singularity, end of story, on a time scale of hours or days, depending on the black hole's size. Meanwhile, an observer who stayed outside, watching you fall, sees something completely different because of gravitational time dilation. You appear to slow down, asymptotically, approaching the horizon but never, from the outside view, quite crossing it, your image red-shifting and dimming until you fade from detectability, smeared out across the horizon, eventually. According to Hawking's calculation, your information encoded into the outgoing thermal radiation over the black hole's entire evaporation lifetime. Two totally different stories. You fell in and hit a singularity. You got smeared on the horizon and radiated away as encoded information. Both true, both complete. And here's the part that used to keep me up at night and still, honestly, does. There is no observer, none, who can ever check both stories against each other, because the observer who fell in cannot signal information back out past the horizon to compare notes with the observer who stayed outside. That's what a horizon is, definitionally, a one-way membrane. Complementarity says this isn't a contradiction because it's not a question the universe ever actually poses to any single physical observer. It's two complete, self-consistent descriptions, occupying regions of description space that can never be cross-examined against each other. I find that beautiful. I also find it deeply strange, and I want to be honest, that the universe never lets you ask the contradictory question is a satisfying resolution logically and an unsettling one philosophically, because it means some of the deepest features of reality are, structurally, hidden from any possible observer by design, not by accident, not by our current technological limits, but by the causal architecture of space-time itself. Let me connect this to something vast, and I mean that as a working scientific claim, not poetry. If space-time really is built from entanglement, if geometry is a low-resolution, coarse-grained summary of an underlying pattern of quantum correlations, the way temperature is a coarse-grained summary of underlying molecular motion, then the question, what is space-time, fundamentally, stops being a question about geometry at all and becomes a question about information. Not information in the casual sense people mean when they say, the universe is information as a bumper sticker. Information in the precise, technical sense. Qubits, entanglement entropy, the specific pattern of correlations among fundamental degrees of freedom that, when you zoom out far enough, looks like smooth, curved, 3+ one-dimensional space-time, the way a fine mesh of individually invisible threads, zoomed out far enough, looks like a smooth sheet of fabric. This is, right now, one of the most active, most contested, most exciting research programs in all of theoretical physics. Figuring out precisely how much of general relativity, how much of Einstein's equations themselves, can be derived rather than assumed, starting purely from entanglement entropy and its behavior. Mark van Ramsdonk showed, in a paper that changed how a whole generation of us think about this, that if you take a holographic spacetime and simply disentangle the boundary degrees of freedom, turn the entanglement down towards zero, the bulk geometry doesn't just change, it tears apart. Spacetime itself rips in two. Zero entanglement, disconnected spacetime. Some entanglement, a thin, fragile connecting thread. Maximal entanglement, a full, smooth wormhole geometry. Geometry is not sitting on top of entanglement. Geometry is a readout of entanglement. That is one of the most important sentences I know how to say, and I want you to sit with how strange it actually is. The distance between you and the person sitting next to you, the raw geometric fact of separation, may ultimately be nothing more or less than a statement about how little the quantum degrees of freedom making up you and the ones making up them are correlated with each other. I want to give you one more piece of honest, productive discomfort before I close. Because a speech that only gives you triumphant answers isn't teaching you what physics actually feels like from the inside. We do not have a working theory of quantum gravity for our actual universe. Everything I've described tonight, Maldasena's correspondence, equals Epper, the wormhole experiment, lives most rigorously in anti-de Sitter space, a universe with negative cosmological constant, a universe that curves the wrong way compared to ours. We live in a universe with a small, positive, cosmological constant de Sitter space, accelerating, expanding, and nobody, not me, not anyone in this field, despite 2 decades of serious effort, has a holographic dictionary for de Sitter space anywhere near as solid as the one we have for ads. That's not a footnote. That's the actual frontier. Everything I've told you tonight about how space-time emerges from entanglement is rigorously demonstrated in a toy universe that is not the universe you are sitting in right now, and extending it to our own accelerating, expanding cosmos, with a cosmological horizon instead of a black hole horizon, is one of the genuinely open, unsolved problems that I think about more than almost anything else in physics, and that I do not expect to see fully resolved in my lifetime. I find that unsettling in the best possible way. It means this argument is not finished. It means some of you in this room, tonight, might be the ones who finish it. Let me go back and fill in something I skipped past too quickly, because you deserve the mathematical honesty behind the word entropy, not just the poetry of it. When physicists say a black hole has entropy proportional to its horizon area, we mean something very specific and very countable. The Bekenstein-Hawking formula says that entropy equals the area divided by 4 times the Planck length squared, and then multiplied by Boltzmann's constant to get it into ordinary physical units. The Planck length is unimaginably small, about 10 to the minus 35 meters, which means that formula is telling you a black hole can store an almost incomprehensible amount of information relative to its size, roughly 1 bit for every patch of horizon about a Planck length across. Take a black hole, the mass of the Sun. Its horizon, its event horizon, is about 3 kilometers across. Run the numbers and you get an entropy of around 10 to the 77 in the appropriate units. A number so large that if you tried to write down a single physical system of ordinary matter with that same volume and that same entropy without collapsing it into a black hole, you couldn't, because you'd run out of room to store that many microstates in 3 kilometers of ordinary matter. The black hole isn't just entropic. It is, for its size, the most entropic object physics allows. That's not a small claim. That's the entire basis for the holographic principle, sitting right there in a formula you could fit on an index card. And it's the reason it hoofed, and I couldn't let it go, because a genuinely maximal information bound, sitting on a boundary instead of scaling with volume, isn't the kind of thing you get to shrug off as a curiosity of one exotic object. If it's a fact about black holes, and black holes are, in a real sense, the most extreme objects gravity permits, then it's very likely a fact about gravity itself, everywhere, all the time, whether or not there's a horizon anywhere nearby. I want to walk you through one more concrete piece of machinery, because I promised you this wouldn't be dumbed down, and the actual teleportation protocol used in that quantum processor experiment deserves to be seen honestly, not hand-waved. Here's the structure. You start with 2 copies of the psych system, call them left and right, prepared in the thermofield double state. Maximally entangled, the quantum state that's dual to an eternal wormhole connecting 2 black holes. In the boundary language, no gravity at all, this is just 2 collections of interacting fermions correlated with each other in a very particular thermal pattern. Now you take a small quantum message, encode it into the left system, and here is the crucial step, the one that makes it teleportation and not just noise. You apply a very specific, carefully tuned interaction that couples the left and right systems together for a brief pulse. Then you evolve the right system forward in time and measure it, if the coupling has the right sign and the right strength. And this is a real, calculable, checkable condition, not a free parameter you get to fudge. The message you encoded on the left reappears, decoded, on the right, faster than it could have if it had simply diffused there by ordinary means, and with a delay profile that matches, precisely, the time it would take a signal to traverse a wormhole, whose throat had been briefly propped open by that coupling pulse, the way Gao, Jefferies, and Wall had shown, in the gravitational picture, that a negative energy shock wave from a coupling like this can very briefly make an otherwise non-traversable wormhole traversable. That's the whole trick. And it's gorgeous precisely because it's checkable on both sides of the correspondence. You can compute the boundary answer with ordinary quantum mechanics. No metric, no curvature, just interacting fermions. And you can separately compute the bulk answer with Einstein's equations and a propped open wormhole throat. And if holography is right, the two calculations have to agree, term by term. When Gao, Jefferies, and Wall first worked this out in 2017, and it agreed, that was, for me, one of those moments in physics where the hair actually stands up on your arms, because you are watching two languages that were invented for completely different purposes, one for particle physics, one for general relativity, turn out to be dialects of the same sentence. You're probably wondering, if this coupling and this teleportation protocol are so precisely specified, why the argument with the Berkeley group is even possible? Why there's room for genuine disagreement about whether 9 qubits actually captured this. Here's the honest answer, and it's a question of scale, not of principle. The real psych model, the one with a genuine holographic dual, needs a large number of Majorana fermions, dozens, ideally hundreds, interacting through a densely connected, essentially random 4-fermion coupling, precisely the structure that makes it maximally chaotic, maximally scrambling, the quantum analog of what general relativity calls a genuine black hole horizon rather than some tamer, less violent object. Current quantum hardware, even the best superconducting processors Google has, cannot yet run that many strongly, densely coupled qubits with anything close to the fidelity you'd need. So the Jefferies-Lokapa team did something clever and, I think, defensible as a first step. They used machine learning to search for the sparsest possible Hamiltonian, the fewest interaction terms, that still reproduced the key teleportation signature the full psych model predicts. 9 qubits, 7 Majorana fermions worth of structure, only 5 terms, mostly commuting with each other, meaning they don't interfere with each other the way genuinely chaotic terms would. And that is exactly the crack Kobrin, Schuster, and Yao drove a wedge into. A small number of commuting terms is about as far from chaotic, scrambling, black hole-like dynamics as you can get while still technically matching the same input-output signal. Their argument, stated plainly, is that you can reproduce that specific teleportation signature using ordinary, boring linear algebra, a simple permutation of qubits, dressed up to look like it came from something scrambling and gravitational, when really it came from something almost embarrassingly simple. I've read their paper carefully, more than once, and I think their technical point about the sparsified Hamiltonian's lack of genuine scrambling is basically correct as a mathematical fact about that specific circuit. Where I think the debate is still genuinely open is the harder, more interesting question underneath it. How much scrambling is actually required before a teleportation signal has earned the right to be called gravitational? And is that a sharp line or a smooth continuum? And if it's a continuum, where on that continuum does 9 qubits, 5 terms, machine learned for exactly this task, actually sit? Nobody has given me an answer to that question that I find fully satisfying yet, mine included. So here's where I want to leave you. And it's not a bow, it's a blade. If entanglement really is the thread space-time is woven from, then the space between any two things in this universe, between you and the stars, between this stage and the back row, between one atom in your hand and another, is not empty, and it is not fundamental. It is a symptom, a large-scale, emergent symptom of a much deeper, much stranger pattern of quantum correlation that has no distance in it at all. No here, no there, no near, no far, until entanglement carves those categories into existence the way water freezes into the specific, brittle geometry of ice. We built a 9-qubit machine that may have caught the faintest possible glimpse of that process, running in miniature, in a lab, in our lifetime. And half the smartest people I know aren't sure yet whether we actually saw it, or just built an extremely elegant mirror that reflected the idea back at us. I don't know which one it is. Nobody does. And if you go home tonight and can't stop turning that over, good. That's not me failing to give you an answer. That's the only honest place a talk about the edge of physics can end.